All right, I'm going to go ahead and get us started. It looks like a lot of people have joined us, and we'll just let people trickle in. I appreciate everybody attending our webinar today, and I'm just going to give you a brief overview of MARICUS, which is, for those unfamiliar, the Mid-Atlantic Regional Association and Coastal Ocean Observing System that I left the S off. Anyway, so a little bit about MARICUS. We power regional understanding and prediction of ocean and coastal dynamics. We are the Mid-Atlantic Regional Association, one of 11 IUs, which stands for Integrated Ocean Observing System, regional associations that are located nationwide. MARICUS covers 10 states in the Mid-Atlantic region, 5 estuaries. Our data serves over 78 million people, and we've made over 50 million observations. And we deliver near real-time data with a purpose. So we have 5 stakeholder-defined focus areas, which are coastal hazards, which we'll be talking about today, maritime safety, fisheries and natural resources, water quality, and energy. And we collaborate with coastal communities, researchers, local governments, and industry to gather and transform raw data into actionable insights from the more than 78 million people who live, work, and visit the Mid-Atlantic. If you have any questions or are interested in partnering with us, especially after you've heard the webinar, we would love to connect with you. Feel free to email us at info@maricus.org. You can visit our website, maricus.org, and you can follow us on social if you don't already. Facebook, LinkedIn, and Instagram, all at Maricus. And with that, I'm going to introduce our speaker today. You'll be hearing from Dr. Scott Glenn. He is a distinguished professor of marine and coastal sciences at Rutgers University. He is one of the founding principal investigators of MARICUS and a current board member. He's also part of the GOOSE, which is Global Ocean Observing System co-design program, and he's the co-lead of the Tropical Cyclone Exemplar. And with that, I'm going to let Scott take it away.
Thank you, Emily. I'll start sharing my screen here, and I'll just take a second to start up. Thank you all for joining us. I saw many people I know on the attendee list, and so you'll recognize some of this. This is the Mid-Atlantic Bight that we're working in, that 1,000 kilometers from Cape Hatteras to Cape Cod. One of the most distinctive features you'll see on there is that wide continental shelf, that shallow region where we work. I represent many people with this talk. I don't know, probably about 100 or so. Many of you are here. You're scattered around, as partners in MARICUS or at NOAA, Navy, Coast Guard, throughout these activities. So appreciate you coming today. We're going to talk about 2 hurricanes there, Irene, which came up our coast back in 2011, and Sandy in 2012, and how they changed ocean observing and how we forecast hurricanes today. One of the things I'll talk about is how we use our ocean observatory in the Mid-Atlantic, our big observatory that we've put together. We came together with the ambition of being one of the most advanced ocean observing systems on the planet at MARICUS. And we did that by making spatial observations. We have a network of satellite dishes along our coast. We have a network of CODAR HF radar stations, one of the largest in the world along that coast, that gives us surface currents that the Coast Guard uses for search and rescue. And we also have one of the largest glider fleets in the world. And we go subsurface for fisheries and water quality. And what we're going to do is use those same observations to look at storms. When we look at this wide continental shelf, we care a lot about what we call essential ocean features. And one of those most important essential ocean features for us in the Mid-Atlantic is something called the cold pool. In the top there, you'll see a cross section from shallow to deep water across that wide shelf. And in the winter, on the left, maybe you see my arrow, on the left, it's cold and well mixed top to bottom. But then as spring comes on, the sun beats down on the surface, it warms it up, and we get this very warm, thin layer at the top, maybe 10 meters, 20 meters thick, but the remnants of that cold water at the bottom. That's called the Mid-Atlantic Cold Pool. This is some of the strongest stratification on the planet. And so it's very important for us to be able to see what that is subsurface. You can't see it from space, so you have to go out there and touch it. And that's what we do with the gliders. We want to see that evolution. And it goes along the entire coast, as we can see in this bottom temperature map. So it's a big feature, about 1,000 kilometers long, unseen until we go out and touch it with the gliders. We're out there for different types of missions, having to do with Coast Guard search and rescue, fisheries, water quality, and every now and then a storm comes through. And because we're there year round, we're there when the storms happen. And one of the most important storms for us was Irene. Here's some of the pre-Irene storm warnings that we were receiving. It was supposed to be one of those storms of the century. Over 2 million people were ordered to evacuate from this storm. President Obama got on TV and on the radio, and he said a historic hurricane, be prepared for the worst. Governor Christie got on TV, and he ordered the evacuation of 1 million people. And in typical Jersey style, it wasn't probably the most thought out evacuation plan, but it was effective. It was simple. Get the hell off the beach. It's time to stop working on your tan. This is a bad storm that's coming. And so with all these warnings of this coming up, people did evacuate. And that was really important. But what happened subsequently as the storm came up the coast, it rapidly weakened. It wasn't a big storm surge event. It was a rainfall event. And most of the rainfall landed inland and caused inland flooding. So we evacuated it away from the coast into the inland, into the area where it was flooding. So there was something wrong with that forecast, and we wanted to learn more about that. Here's a picture of Irene coming up the coast along that track, along our coast, going through our, approaching our HF radar network. And you can see that there's that 1,000 kilometers worth of CODAR sensors along the coast, giving us the ocean currents at the same scale as the storm. So that's unprecedented. We also had below that, we had the gliders flying. 2 gliders, one coming down from the north from the University of Massachusetts and one from Rutgers on a water quality mission for New Jersey DEP. As this storm was approaching, right, storm of the century, our friends in Woods Hole were pulling their gliders out, and they called us up. What should we do? And we said we were leaving them in. The New Jersey Department of Environmental Protection said, leave the glider in. We're going to learn something. We don't know what it is, but leave the sensors out there. And so we left the CODARs on the beach. We left the gliders in the water and to see what would happen. And this is the story that quickly unfolded as it was coming north. If we look at the satellite imagery, pre-Irene, there's a very warm ocean out there. It was summertime, and the ocean's getting warmer, so it's a very warm ocean. That was feeding the hurricane models, and they were predicting things like Cat 4 hurricanes coming into the New Jersey coast. Post-Irene, a very cold ocean. Somehow that ocean cooled during the passage of Irene. Sometimes, in some areas, that cooling was as large as 11 degrees centigrade. That's huge. 1 degree centigrade change makes a big difference to a hurricane. And here we have an order of magnitude difference. But with satellites, you only know before and after. There's clouds covering it during the event. So we don't know what happened then, except we had the glider out. And so here's a picture of the glider cross section where we have depth on the y-axis and time on the x-axis. And we look over here on the right-hand side of that plot, left-hand side of that plot, and it's warm at the top and the cold pools at the bottom. And as time goes along, we see there's cooling and deepening of the thermocline. And we hadn't seen that before. And then we have eye passage. And we look at the time of the eye passage, instead of going over that warm water, that that hurricane went over very cold water. And we know that hurricanes over warm water get intensified, hurricanes over cold water get weakened. And so somehow there was mixing going on that happened before the eye went over. So it's ahead of eye cooling, and that weakened the hurricane. And we didn't expect that. We also didn't know why, but we have an observatory, and that's where we look at the HF radar currents that we had from the CODAR systems, where as the eye is approaching, those strong winds were forcing all the water onshore, that surface water. And so you see that area, that arrow is going towards the coast. And since the glider was seeing no net velocity top to bottom, there had to be a counterflow coming back the other way. And the two of those produce shear, and that shear mixes across the thermocline and cools. Nobody had seen this process before. We had talked about this at an ocean sciences meeting for the first time in Utah. And the head of NOAA walked up to me after that and said, hold on to this. This is very significant. You are going to get pushback about the ocean evolving as quickly as a hurricane. People don't know that yet. You will get pushback, but this is physics. Keep pushing this forward. And so we followed that advice. And it didn't take long for us to have to apply that again. Hurricane Sandy came in 1 year later. And again, we're starting to send out warnings, storm of the century, those kind of things. And we had cried wolf the year before. It took extra time to convince people that Sandy was for real. We had so much warning for Sandy. I was down at a conference in Brazil talking about Hurricane Irene 7 days in advance, and a big storm was coming. And that was the warning we gave. I still had time to, fly up to Chicago to my daughter's college parents' weekend, get back to New Jersey, board at my house, and then sit and wait for the hurricane to come. But Marcus, while I was doing all that, prepared the network. So they did the work. Some of those students are possibly on the phone, people like Travis and Greg. One of the first things we did was prepare what we called a hurricane glider. We had never done one of these before, but we took one of our gliders and we strapped with hose clamps an ADCP, a current profiler, onto the front of that glider because we wanted to look more at those currents to see that ahead of eye mixing so we could see that cooling and see how Sandy lost, was going to weaken before our very eyes. And so we put the glider out with that ADCP strapped on with hose clamps. And here's that picture of Sandy way in the south, coming up, making that left-hand turn. The glider is deployed inside the CODAR network on the right-hand side of the storm, the most intense part of the storm. So the network was perfectly set up to capture that storm, and we were going to watch the head of eye cooling come in. And so here it is 2 days before landfall coming into our coast. If we look at this temperature time series in the bottom, warm at the top, cold at the bottom, everything's all set up. We're ready. And we look a couple days later, the morning before landfall. Here it is coming into the coast just before, it damaged everything as it was coming in. And we look at the temperature profiles coming from the glider. And suddenly the cold water had gone away. It's the morning before the hurricane is going to hit. There's no cold water. We're looking at this, we're saying, there's no cold water to mix and cool and weaken Sandy. Sandy's going to come in strong. This is not what we expected. Who do we tell? There was nobody to tell. It was coming in that day. There was no way to communicate this glider information to the warning centers that could use that at the time. So that was our first concern. And then the strong winds hit. And in my backyard, I heard that snap, that snap of the big trees, the 30-inch diameter trunks as they snap like match twigs and scrape against the house. And we're talking to each other, saying, we have to survive this storm. Let's get off the internet here. and survive the storm, we have an important story to tell to get this out there. Here's some of the pictures from that storm. The upper right there is from my hometown. All the telephone poles knocked down along the main street, but the flooding we saw along the coast, totally devastating storm, totally unpredicted. And so these back-to-back storms illustrate the problem that we have with hurricane forecasting. We had a lot of warning, about 5 days for Irene, 7 days for Sandy. And we had pretty good track forecasts, but the intensity was way off, and we had no idea why. If we look at the track error, this is back in 2012, right after the hurricane, after Sandy, we see track errors over the last 20 years constantly decreasing, better and better. We have better global models, and the steering currents telling us where the hurricanes are going. But the forecast intensity, those errors, they remain flat. We weren't getting any improvement in those. One of the things that we knew is that, well, we need better ocean observations in there. When we added into the ocean to our hurricane models, the forecast actually got worse. So there was more going wrong than there's the bad ocean. There was a lot to improve, because if we put a more physically correct ocean in there, the forecast was not getting better. That was when the research activities kicked in. And so not only does NOAA, through IUCE and NOS support the ocean observations, through OAR, they also support the ocean research. And through SINAR, the universities along this coast work together to develop, go beyond that prototype hurricane glider that flies under the HF radar. Let's build a real hurricane glider, test it, and see if we can assimilate into the models, improve the models, and do the science of what actually happened. And that's where we had people like Travis Miles and Greg Soroka, I think some of them are on the call today, working on this in this very room, working on this as part of their thesis to come up with what really happened during these storms. And just a couple slides on what happened during Irene. If we look at what happened with the ocean, we saw that ocean cooled over time. What happened in the atmosphere? If we use a static ocean, like many of the models were doing at the time, we'd have that warm ocean boundary condition, and we look at the atmospheric model results that would come from that, we get a very strong hurricane coming up the coast, something like a Cat 1. If we let that ocean evolve into that cold ocean ahead of the eye, so that the eye is going over cold water, we get something like a tropical storm. So 10 knots or so difference. And so instead of a hurricane, you get a tropical storm, much more like what was observed. And if we look at those observations, that cold sea surface temperature forecast of the winds, we get something, here's that cold run here, something much more like the observed storm surge. And we can trace back all the different processes in the ocean, including how the mixing occurs and what kind of mixing, what kind of eddies are formed to do that mixing. And we now can go beginning to end of the ocean response impacting the hurricane and going on to impact the storm surge. One of the things that OIR said they needed, this was Craig McLean, the head of OIR at the time, says, I need you to document this in a stack of papers that we can point to that says, this is why we need to do this. And so, these are hard decisions. They cost money. We have to have good documentation. And so we did that through that research money funded through OIR. And we documented this ahead of eye cooling and mixing that we saw in Irene. It's the first time this was done. So this was like a discovery paper. We made it into Nature with this. We also observed this in 10 other mid-Atlantic hurricanes and 2 other typhoons in the Yellow Sea with our colleagues in China. So this is not just one storm in the mid-Atlantic. It's like many storms in the mid-Atlantic, also in places like China. We also looked at the sensitivity to those models to the all different parameters in the ocean and the atmosphere and the mixing and all that, and found, a 130 member ensemble. This was Greg Soroka's work. Only the ensemble members that allowed the ocean to cool and had that cool ocean in it, those were the only ones that could match the observed weakening and then the storm surge that happened afterwards. And so this is the critical process to get that. And then we looked at the detailed evolution of the ocean and how it co-evolved with the atmosphere during that, in both Irene and Sandy. And with this research put together, we took all of this down to AOML in Miami, and we sat with the head of the hurricane forecast improvement, and Gerhard was with me. And instead of like a 20-minute talk, he had to sit through a 3-hour talk where we talked with the head of the hurricane forecast improvement program about the importance of the ocean and showed him all this evidence. And at the end, his reaction was, "You have produced irrefutable evidence that the ocean and atmosphere during the intense forcing of a hurricane can co-evolve and affect each other." And that was the step we needed in 2017. Because in 2018, we then began the Hurricane Glider Program in earnest. There was work going down in the Caribbean through AOML, our work in the Mid-Atlantic. We brought all that together in all 4 IU's regions, from Caracus to Jicus to Sakura to Maracus, up and down the coast, and coordinated the hurricane glider picket lines, as they were called. We identified essential ocean features along the hurricane pass. You see the hurricane pass over there on the right, and the whole tracks are gray, and we turn red the last 5 days before landfall. And so you can see that if you want a 5-day forecast or even a 7-day forecast, which is what we want to look at, those hurricanes are way south. Many of them are over the Caribbean or in the waters of other countries. And so this is a large area that we have to cover. And we want to identify the essential ocean features along that whole path, like the heat that we have in the Caribbean, the freshwater inflow from the Amazon and Orinoco that make barrier layers, the loop current in the Gulf Stream in the South Atlantic. In our region, it's that seasonal stratification, that cold pool that we have. We had these essential ocean features, and we developed the means to sample them with the gliders. And we have our different concept of operations than the hurricane hunters might have. And we use a soccer game analogy there, where, like, if you're the hurricane hunters, you dress up in white and you fly through the air and you chase the ball, as you're shown there. But if you're one of the hurricane gliders, you're not chasing the hurricane, you're defending the goal. You're standing between the hurricane and the homeland. And that's your job. Was when the hurricane comes over, you've already been there for several days, getting the ocean right before the hurricane arrives. And so that's their job, is to play the goalie. And we even use the IU's glider DAC as a way to anybody with a glider can come in and send their data in and have it contribute to the hurricane forecast. So no matter what mission they're on. So it's a true community effort that we put together. You don't have to be a specific hurricane glider. Anybody can join. And here's our operations overview from 2024, the last hurricane season that we had, 104 deployments. And you see the long picket line along the East Coast from, Texas all the way up towards Cape Cod. And we also see the U.S. waters around Puerto Rico and the Virgin Islands are covered quite nicely. There still is a big gap in this area where we saw the tracks over the Caribbean in those other those waters that are in other nations' jurisdiction. So that's something we're going to work on with the global people here. And if we look at our statistics over the years since 2018, the number of glider deployments has increased, 104, and the number of days at sea have increased over time. So we're continuing to maintain these hurricane gliders out there, getting these essential ocean features, getting that data to the models so where they can assimilate it and prove the ocean model in our coupled forecast systems. That gap. We saw a lot of those red tracks over the Caribbean, but there's a gap, and how do we close that? Well, those are international areas, and so we go to the Global Ocean Observing System, and they have a co-design program. And in that co-design program, you work with the different users and you figure out what is the best way to improve the observing system for the needs we have. And so for our tropical cyclone exemplar that I work with Cheyenne Steinberger at NOAA, we work on co-designing this global ocean observing system so we can improve that understanding and forecasting of tropical cyclones globally. One of those examples of the successes is shown here on the right. This is, I think Lev is on the call there, where he coordinated that Navy P3, not the NOAA P3 flight over the Hurricane Hunter, over the glider, and had the co-deployed atmosphere and ocean sensors together. And so these are the kind of coordination activities that we've been doing. And how do we use that to go forward with GOOS? There's a lot of sensors through research, a lot of that at NOAA OAR, that we know will improve hurricane prediction. And so which ones do we focus on? What are the most important things for us to do? For that, in the co-design process, we look at this, the value chain, going all the way from the research scientists through the operational models, through the people that have to respond, where the data flows in one way and the requirements come back the other way. And we see what kind of data sets they need. And the most important requirement that came back, the biggest data gap we saw, was there from the Environmental Modeling Center where all the models were run. And they said there's this dearth of subsurface data. We have to get that subsurface data in to get the right ocean under the atmospheric models. And that's really important because we have a whole ensemble. We have hundreds of atmospheric models, but we only have one chance to get the ocean. They all use the same ocean. So we need to get that right. We need to get that right, not just for us, but globally. And that's part of what we do with the tropical cyclone exemplar, is look at all the different regions where the cyclones are important and come up with what can they contribute to this effort. And there's the tropical Americas and Caribbean area, where we need to do that capacity building for these most damaging of tropical cyclones. And through that effort, here's what the map looks like for 2025. It's much more filled out because of the collaborations through the Global Ocean Observing System, Tropical Cyclone Exemplar, and through groups like IO-Carib, the regional alliance for it within GOOS. We're building the collaborations to move between EEZs for the first time with the gliders. We don't have to just stay within our own US waters. And you can see that there's our usual US water area. We're including the Barbados area where we get the inflow from the Amazon and Orinoco, a section between Dominican Republic and Curacao, the Jamaica area, and then with our Mexican colleagues over by the Yucatan. And we also are starting to work on the plans for put together the HF radar network, just like we have in Maracus, for the inflow along the Antilles and the outflow in Yucatan. So we have the same network that we started with in Maracus, HF radar with gliders flying underneath it in this Caribbean, so we can improve those hurricane forecasts many days in advance. So my summary, Irene and Sandy, disruptive events. They disrupted the environment, they disrupted our science, and they disrupted how we do operations. We were there before, during, and after those events. And we continue to work on this and make a difference in the lives of lives of the people, the safety, security, and prosperity of the American people. And so what I'd like to do now is turn it over to Mike Crowley, Technical Director from Arcus. He's going to talk a little bit about what we have planned for the Mid-Atlantic for this summer. You saw the plans for the Caribbean. Now Mike will talk about the Mid-Atlantic.
Right.
Mike.
Thanks, Scott. Scott, you can go to the next slide. So briefly, just an overview of kind of what the IUS view is. We have these weekly calls now during hurricane season where all the crews operating gliders, and we call it the hurricane glider call, but all the crews operating gliders for any reason, we all get together every Monday, and we talk about the different deployments and things that will have operations and what's going on and what science interesting things are happening. So over the course of hurricane season, we've got overall in all these regions about 45, maybe as many as 50 deployments scheduled. All those little lines, whether they're Navy gliders in the yellowish or different funding supported gliders in blue and pink and brown and green there. Those are all planned glider deployment locations for all the different regions along the coastlines for this summer, which started 10 days ago, 11 days ago. All right, next one, Scott. And from the Maricus perspective, and this really bodes for everybody, it's all about partnership. And we have a lot of partners within Maricus that have funding from all sorts of different groups. We have about 12 deployments planned in the Mid-Atlantic this summer. A couple are out right now. A few of these are Maricus funded, and the rest are different state and local funding that makes these gliders available. It's all about the leveraging and the partners. A glider doesn't have to be a quote unquote hurricane glider. If it's got temperature, salinity, and depth on it, which they all do, that gives us the information that we want to see what's going on in that coastal ocean, to see if we can make out that cold pool, if it's where the location is, where the boundaries are, how deep it is, how cold it is. So all these gliders can be leveraged to help support these hurricane forecasts, no matter what they're funded to do, whether it's listening for whales or doing monitoring around wind turbines or whatever the case may be. We can leverage these for looking at hurricanes. One, they are not single focus use. They are multi-use. Whoever's looking to use the data, and all that data is made available through the IUS Glider DAC. And very close to real time. So that's kind of a little bit of a plan of what we have this summer into late October. That's it.
Thanks, Mike. Back to you, Emily.
All right, folks, if you have, we have some time for some questions. So if you could go ahead, if you have any questions, just put them in the question and answer icon on the toolbar, and we will get those answered. Okay, Scott, what are we doing to improve the models this year?
Okay. Every year we work a lot with the Environmental Modeling Center at NOAA. NOAA EMC is where they run the models. And so we work with them to look at how the data is getting assimilated and before and after the assimilation and how that improvement occurs. They always have two models that are running in parallel. One is the operational production model, and the other parallel is an experimental one where we can work and tweak different aspects of it. And so some of the important things that we're doing this year is we're looking at the trade-offs in how we assimilate altimetry versus how we assimilate the glider and Argo data, the profile data. The models are very good at all the models are very good at assimilating profile data. Many of the models are different in how they assimilate the altimetry. So we work with them to try to improve that. And we have two different versions of the altimetry assimilation. We're looking at how that will improve our Central Ocean features and how the the timing that we have for the glider data coming in, how that improves things. Argo's on a global climate mission, so the data comes in often once every 10 days, whereas glider data is being reported several times a day. And so it's kind of this layered approach. Far away, Argo's given us the climate scale, a very important job. And then as you get closer to the coast, you have the gliders giving more rapid updates. So we're balancing all that. All that feeds into the new hurricane, the HAVS model, which is a coupled model, and they improve that every year. And so we're trying to get that one best ocean into the ensemble of many hurricane atmospheric models.
Wonderful. Thank you, Scott. Another quick question is, what are steps that Goose is taking to make improvements this year?
The big steps we have in Goose, most of them are occurring in the Caribbean for us. They have the regional alliance, IO-Carib, and that's been revitalized lately through the Ocean Decade. So that Ocean Decade work continues. They're building a multi-purpose observing system, observing capability for the area. And they have different priorities. And so one of their priorities is, of course, hurricanes, as it is in others, like Asia. They have those priorities. And so through groups like the WMO, the World Meteorological Organization, where they have the Hurricane Committee, and that Hurricane Committee meets to discuss, what are the improvements we need. We see the collaboration between the WMO and GOOS growing over the last 2 years, and GOOS being the place that, okay, how do we get these gliders out there? How do we get permissions to cross the international boundaries? And how do we get those to the operational centers? And that combined presence of the WMO and the IOC together is a pretty powerful international force. The WMO knows that if they need a better ocean, they go to GOOS, and GOOS knows that one of their best customers is the weather people. Thanks.
Wonderful. We have another question. How will recent departures of personnel at NOAA impact what you do and the data you collect?
Yeah, there's already people shortages in many of the activities that are associated with weather forecasting already. So that's already an issue. There's this very important need to prioritize. There's going to be less coverage for sure. And luckily, the gliders will still be out. We still have some of that funding is still in place, and there's still interest in keeping the hurricane gliders going. The people we work with, once we get that data to shore, there's fewer of those, so that it makes that a little harder. And so advances, technological advances will be slower. There's no way around that. With fewer people, there's less time to put into advancing what we learn every year. And we're especially worried about losing the science. I'd really emphasize today how important OAR, the Ocean Atmospheric Research, was to produce those papers that you could point to demonstrate that there's an important return on investment, and there's going to be less research. So that'll slow progress. Thanks.
Thank you. We have another question. NOS is developing a new Northeast Coast operational forecast system, which covers from the Chesapeake Bay to the Gulf of Maine. How can we access the glider data for model validation and data assimilation?
Yeah, I use glider DAC. It's the most direct way to access that. We've set up that glider DAC to be the central place that all the glider operators can put their data and then provide access to others. So that's the quickest, most direct way to access it. Also, from the glider DAC, it goes down the much more complicated route to get to the GTS, where NDBC harvests the data like hourly from there, does their own quality control, puts it on the GTS, and then it can go to all the other operational centers. So if you're one of those operational centers, you can also get it through the GTS and pull it from there. But I'd go straight to the glider DAC. That's the original source.
Great, thank you very much. Have you seen any of the NHC discussions where they mention glider data and any anticipated mixing from the cold layer just below the surface impacting hurricane intensification or weakening? Do you envision more NHC operational use of glider data?
I've seen those discussions of the cold water below the surface. If you look at the National Hurricane Center website, for each of the forecasts, you can read the discussion that the forecaster prepares. And not every forecaster does, but you can read those. And I'm always looking for cold water below the surface and mixing as the storm is approaching. And you do see that. So I see it more and more frequently is what I look for to see that what we're doing has an important impact. And what I'm looking to do now is see more talk of like the barrier layers, the surface, the rivers that are impacting the surface, the fresh water and slowing the mixing and increasing the intensity of the storms. So we are seeing that come into the Hurricane Center. And what was the second question? The second part of the question?
Sorry, let me go back to it real quick. Do you envision more NHC operational use of glider data?
Oh, yeah. Yeah. They said the most important way for them to use it is to have it assimilated into the models to improve the forecast. This is the first thing they told us was make sure it gets to the models, because the most important job you can do is improve the model forecasts. But as more and more data sets are available and people get used to it, and you get it into their operational system, they're very busy people. They have a lot on their mind and they're making very important calls. So they can't be going around searching for the data. You have to make it available as a product that they look at. And so some of the important things they like to look at are ocean heat content. How much heat is in that ocean above like the 26-degree isotherm? And so new ways to present that to them in their operational system is something that I know they would appreciate having. Thanks.
Thank you. And we've got one more question. Is there a unified HF radar product that we can access as an overlay in our GIS systems and tell a broad/regional story to decision makers?
Yeah, there's just like there's the IUS glider DAC, there's the IUS HF radar DAC that is undergoing its transition over to NOAA NESDIS as we speak. And so it's becoming an even more operational product by that transition. So National HF Radar Network, National Glider Network, just like we have in the Mid-Atlantic, you can access both of those through IUS, and both are very useful tools for that.
Wonderful. Thank you so much, Scott. We just want to take time. That's all the questions that we got.
Okay.
We will just want to say thank you everyone for attending. All the information for this year's hurricane gliders for Maracus will be available on Oceans Map. There is a data layer on there that you can look at that as those gliders go out and do different predictions. And we just want to say thank you again for everyone attending. And if you don't already, please join our newsletter or follow us on social media because we'll be doing more of these webinars in the future. So thank you very much. And thank you, Scott and Mike. We appreciate your time and effort, and what a great story. And we really appreciate you guys telling it.